Hello, my name is Danny Nowlan and I'm the Director of ChassisSim Technologies. Welcome to this latest episode of Dan's Vehicle Dynamics Corner. In this episode of Dan's Vehicle Dynamics Corner, what I'm going to be talking to you about is calculating the stability index from lateral accelerometers. And might I just say, I'm really excited to be giving this tutorial. And the reason I'm excited to be giving this tutorial is for two key reasons. Number one, the stability index is something that I have spoken about in my articles in Racecar Engineering and in this forum on Dan's Vehicle Dynamics Corner for a number of years. But the calculation of the stability index has always been one of these things. It's always been a little bit tricky and it's been a little bit hard. But a colleague of mine was really good, was very gracious to share some data with me to shed some light on this situation. And I'm really glad to be able to present this to you today. So let's get started. We're going to discuss and review the concept of the stability index. We won't spend too long on that, but just enough to refresh your memory about it. And we'll then discuss a really useful approximation of yaw moment. And then what we're going to do to discuss is we'll discuss techniques to calculate the stability index. So let's get started. As we have discussed on a number of occasions before, the stability index has its origins from the concept of the static margin in aircraft longitudinal dynamics. And the whole idea with the stability index is what we're measuring is we're effectively measuring the moment arm of the center of lift of the car, or center of lateral force the center of lift of the aircraft, or the center of lateral forces of the car, and we're measuring that moment arm to the CG. And effectively, if it's behind the center of gravity, the car is stable. That is, if you give it a disturbance like a steering input, it goes over some bumps, and if it gets disturbed from where it's going, it will eventually stabilize itself out. If it's right on top of the center of gravity, it's neutral. You give it an input, it'll keep on going. And if it's greater than the center of gravity, if you give it a input, it will just keep on going. Now, this is pretty much part and parcel of what is drilled into you if you're an aeronautical engineer. And I can tell you right now, I had it drilled into me for nearly 2 years. And in some respects, this is the ultimate measure of race car stability. Now, the automotive incarnation of this, the stability index, is effectively expressed as the derivative of lateral moment divided by the derivative of the slope of yaw moment of lateral acceleration divided by the total mass of the vehicle times the wheelbase. Now, you'll see here that I've given you an example of how to calculate it from first principles if you've got a tyre model. And for those of you who are interested in terms of the whys and wherefores and some examples of that, I would definitely refer you to my book, The Dynamics of the Race Car. But effectively, what the stability index is it's effectively the difference between initial tyre curve slope at the front multiplied by the center of gravity divided by the total change of force over slip angle of the whole vehicle. But I will let you sort of chase up my book, The Dynamics of the Race Car, or Millikan Race Car Vehicle Dynamics, to really drill in to what we want to do. But effectively, what the stability index is effectively the way we measure it is we measure the slope of the change in lateral moment over the change in lateral acceleration. That is basically the heart of what the stability index is, and that's where we get that measure of the difference between the center of the lateral forces or the center of aerodynamic forces from the CG. Now, the tricky thing when it comes to determining a stability index is getting a good read on what lateral moment is acting on the car. Now, this is typically where things get really, really tricky. However, here's a magic trick. If you've got lateral accelerometers mounted on both ends of the car, you can approximate the lateral moment of the car as basically 1 minus the weight distribution of the front times the lateral signal at the front minus the weight distribution of the front times the rear lateral accelerometer multiplied by G, which is acceleration due to gravity, times the wheelbase times MT. That will give you the lateral moment of the car. Now, to talk about, now, I have heard some discussions questioning the validity of this, and this is basically where this race data came in. So, as we can see here, what we've got here is this is this is basically a plot of speed and front and rear lateral accelerometers from a mid-engined GT3 race car. Now, in this particular car, effectively the bulk of the masses were pretty much in the center of the car. There was a bit hanging over the rear, but the front basically pretty much with these sort of cars doesn't have an awful lot on it. But we can see very, very clearly here the front lateral moment is in blue. The front lateral acceleration is in blue, the rear lateral acceleration is in purple, and you can see very clear and distinct differences. That is pretty much ironclad proof that this equation here for our lateral moment is in fact valid. So to me, it was one of these things that when I saw those questions, I did go away, have a good hard think about it, and obviously I asked a few of my customers for clarification, and one was very gracious in getting back to me. In particular, given that it was a mid-engine car, I just figured, yep, that is hook, line, and sinker. The other thing too that I'll also throw out there as well is just remember the way a lateral accelerator. An accelerometer works in a number of different ways. But the most common of all is that you've got a piezoelectric device that the millisecond it starts to get moved, it starts to get moves or experiences an acceleration, it starts to move, and that's exactly what will happen on both axles of the car once you start applying a force to it. In particular, once they're balanced into a turn. Is this perfect? No, but if I can really leave you with one thing, when it comes to looking at data, nothing truly is perfect. However, the fact that you've got such clear and repeatable differences here is pretty much a very firm indication that this, at its very least, is an excellent approximation. And I can tell you right now, I'd look at that and I would just go, yep, we're definitely going to get a significant way down the road with this. So what we now need to do is we need to do an XY plot of this. So what we need to do is we do an XY plot, and we're looking for the slope of the plot. Now, as we can see here, we've pretty much done this unfiltered. So the horizontal axis is lateral acceleration, the vertical axis is lateral moment. Now, I should add a little bit of an apology here. The units here should be actually Newton meter per G as opposed to Newton meter. I basically put together that math channel in a little bit of a hurry. But you can see here, even though there's quite a bit of noise at the edge of the edge of when we're starting getting into peak lateral G, you can see, particularly when the acceleration is between plus or minus 0.8 of a G, we've got a very, very clear, distinct line emerging. Now, the other thing that I want to say here is this particular car had positive lateral acceleration as a left-hand turn. So consequently, we've got a positive gradient here. This indicates that we have stability. If we had a positive, if the lateral acceleration was positive for a right-hand turn, that curve would be the other way around. So I really want to ram home that. Point. So looking at that slope, you'd look at it and go, you know what? That's not the complete deal. However, we're certainly on to a good start. So what we now need to do is we need to have a bit of a think about the data and what we can do with it. So to refine our results, what we want to do is the first step in this process is to filter the yaw moment signal at 4 Hertz. Now, the reason that we're going to filter the yaw moment signal at 4 Hertz is basically most of what you'll be looking at in terms of what the driver is going to feel through his pants is going to happen between the 0 to 5 Hertz frequency range. Now, a really good proof that you can do for this is if you put together a simple bicycle model and take a look at the eigenvalues and eigenvectors, you'll actually find that they will fall between the 1 to 4 Hertz range, particularly in the yaw moment mode. Now, I realize a bicycle model is a bit rough, but that indicates the sort of frequencies we need to be considering. Now, as we can see from our figure here, all of a sudden, that plot, in terms of its linear trends, improves considerably. Now, what we've got here is we've still got our very strong trends between plus or minus 0.8 of G, but as you can see, we've significantly tidied it up as we've significantly tidied up where we've got big values of lateral acceleration. Now, I did a curve fit of this using Microsoft Excel, and the slope was 295. That's the slope of Newton meter per G over AY measured in G, and the R squared value was 0.55. So we're certainly on to a very good start here. We've now got a pretty clear trend. It's not ironclad yet, but it's a pretty pretty clear trend. The other thing too that I want to point your attention to is if we basically do a plot, you'll see the best line of fit is pretty much slap bang in the middle of the data, which shows that we're definitely onto a good thing. So let's take a look at refining the results a little bit more. So what we're going to do here is we're going to filter the yaw moment signal at 2 Hertz, and we're going to filter the AY signal at 10 Hertz. Now, when we did this for the raw data, let's take a look at what we're looking at. What I want to point your attention to is the 2 last plots. The last plot is yaw moment, and the very last plot is G-force. As we can see, we filtered out a lot of the spikes in the G-force signal, but more importantly, take a look at what we've done with the yaw moment signal. Even though we filtered it at 2 Hertz, you can still see some pretty clear trends in terms of the fact that it's not a complete straight line. That indicates that we've still got a bit of the behavior of the car happening there. So we actually haven't actually totally and utterly filtered out what's going on. In particular, if we're trying to get any sort of sloping trends, one of the clear signals that you've gone too far is the fact that if you've filtered it, if you've over-filtered it, it just comes as pretty much an overly straight line, and that falls into that category. If something is too good to be true, it probably is. So what we did was after we applied that filter at 2 Hertz, we did another plot. Now, as you can see here, we now have a definite straight line emerging, and that, ladies and gentlemen, is the stability index. So when I when I exported that out into Excel and did a curve fit, the slope was 293, so I hadn't changed that much from what we had done when we'd filtered the yaw moment signal at 4 Hertz. But this time the R squared value went from 0.55 to 0.74. Now that shows us very, very clearly that we're onto something really, really good. One thing I do want to just have a quick chat about, particularly for some of you who might be who might be a little bit skeptical. One thing about evaluating yaw moments, because of the very nature of what they are, they're going to be they will be very, very messy, because at its heart, it's effectively a second derivative. And second derivatives and derivatives by their very nature are very, very noisy signals. And we factor into that, we've got cars going over bumps, we've got drivers modulating traction with the throttle, and various different steer inputs. There's going to be a bit of a spread in the data. However, what we're after here to evaluate the stability index is we're after a clear trend. And we could start to see that trend emerge from looking at the raw data, particularly from what we were looking at in here. Once we filtered that, we could definitely start to see a straight line emerge. And when we filtered at 2 Hertz, what we found is that we could definitely still see the variation in the yaw moment, which had definitely taken that edge off. And once we did the XY plot, all of a sudden we're seeing a very, very clear and distinct straight line. So, and that straight line, ladies and gentlemen, is the stability index. Now, let me also sort of add to this. I'm about to release a Racecar engineering article about this, which will be, if it's not released this month, it should be released the next coming month, where I probably do a bit more of a complete analysis of this for you. However, this is a clear indication that we've definitely got a very clear and distinct trend happening here. So consequently, this is something that should definitely be part of your engineering toolbox. And to be quite honest, as far as I'm concerned, if you're really serious about evaluating what the driver is doing, let's put it this way: I think you'd be crazy not to have AY sensors at both axles of the car, because a number of my colleagues in the ChassisSim community have actually found that to be a really good sanity check to make sure that the drivers aren't leading them up the garden path. In terms of some finishing touches, now all we need to do is calculate the value of the stability index. So all we did was we take our dnday that we'd calculated out from our Excel curve sheet, and we simply divided it by the total mass of the vehicle divided by the wheelbase. In this case, it was 1,340 kilos divided by a wheelbase of 2.675 meters, which means our stability index is minus 0.0825. So that basically means that the center of the lateral forces is 8.25% of the wheelbase behind the center of gravity. In summing up, the stability index can be calculated from accelerometers, or at least we can get a very good approximation of it. The key to making it work, though, is to filter the data, but filter the data intelligently. Don't overdo it. And I would strongly suggest you play around with what works best for your car. And I can tell you right now, this is something very much worthwhile you pursuing. Do you, for instance, take out? Does this necessarily mean you throw away all the other ways that you've been determining car stability? Of course not. This is something that will complement what you're already doing very, very well. And in particular, one of my tools that I always use to evaluate race car stability is comparing the neutral steer plot versus the actual steer plot. That tells me a wealth of information of what's going on. And particularly if the car is being driven at the edge, the neutral steer versus actual steer plot matches up very closely with the stability index. So if you know that the neutral steer and some rough rules of thumb here, if you know the neutral steer and actual steer plot and the yaw moment versus lateral acceleration plots are showing you the same things. For example, if you've got a car that's understeering and you see this sort of slope, you know that's a setup problem. It's something that it's up to you as the engineer to fix. If you've got things that are telling you two different situations, then that's something that you need to dig a bit deeper. However, the next step I now leave with you guys. Throw some mud on the wall, put some lateral accelerometers on both ends of the car, play around with your filtering. Do some setup changes, or go through some old legacy data, and find out for yourself and explore around for yourself what a valuable tool this can be. And we'll catch you on the next episode of Dan's Vehicle Dynamics Corner.